Okay, this question contains another piece of bent wire, um, and it is actually quite a simple question if you know what the diagram is representing. What it's representing is a situation like this. This sheet of paper here is the XY plane. Coming perpendicularly out of that is the Z-axis. Now I've not put the Z-axis on here, but I've just put the three pieces of wire. So this black pen here is meant to represent the piece of wire from A to B. The red pencil is representing the wire from B to C. And then this red pen here is representing the wire from C to D. These dots here represent the fact that the magnetic field is coming perpendicularly out of this piece of paper, or out of the XY plane. So the magnetic field lines here are pointing vertically upwards. Okay, so that's what it represents. So if we wanted to figure out, say, the direction of the magnetic force on this section of wire here, well, we would have to, we know the current is this way, right? So we'd have to apply the right-hand rule. So we'd point our thumb in the direction of the current, our fingers would go upwards in the direction of the field, and then the direction of the force would be across this way. Okay, so the force would be out this way here. We know that the direction of force has to be perpendicular to the direction of the current and to the direction of the magnetic field. And from the right-hand rule, I can see it's like out that way, like that. For this piece of wire here, we apply the right-hand rule again. So we put our thumb in the direction of the current, our fingers in the direction of the field, which is vertically upwards, and then our palm, well, it's kind of hard to see my palm. The front of my hand is going to point in the direction of the force. So the direction of the force on this red pencil piece of wire is out this way, perpendicularly to it. So yeah, I mean, if I was to draw force vectors on for these two guys, we would have like one magnetic force, which is up this way. So that's the direction of the magnetic force on this guy, and the direction of the magnetic force on this one is going to be out here, like this, and this is a 90 degrees, 90 degrees. Now this red pen here, this also has a current in it. However, remember that the magnetic field lines are coming perpendicularly out of the page. So that means that this section of the wire here is going to be parallel to the magnetic field. So this is not going to be experiencing any force at all. There's no magnetic force on this wire because it is parallel to the field. All right, so now that we know the directions, let's go back and figure out the magnitudes of the forces on this guy. And in fact, we can see in this case, when we come to calculate the magnitudes of the forces, it's going to be really simple. So we don't really have to worry about angles, because this piece of wire here is perpendicular to the magnetic field line. So the angle between this current and the field is 90 degrees. The angle between this current here and the field is also 90 degrees. And the current and the angle between this current here and the field is 0 degrees. So no force, and maximum force. All right, so with those forces just drawn on this diagram, then it looks kind of something like this. So FAB is out here in the XY plane, perpendicular to the wire and perpendicular to the magnetic field, which is pointing upwards in the Z direction. Same with BC. BC is also perpendicular to a section of the wire BC, and this is also supposed to be in the XY plane. Okay, and section CD is parallel to the Z, so this is the one pointing straight up. So let's just figure out the magnitude of the force on these two guys. So, I mean, first of all, I can say this. I can say, well, the angles that both bits of wire make with the field are 90 degrees, right? So let's say that. The angles that, let's see, we got AB and BC. You say make with the field are 90 degrees. So therefore, the force for the the formula for the magnetic force becomes quite simple. So we don't even really have to worry too much about angles. Just chuck in 90 and the sine theta becomes 1. So FAB, the magnitude of the force on y section AB, is equal to the magnetic field strength times the current times the length of wire AB. And that's it. I mean, well, right, so we could chuck in sine of 90, but that doesn't do anything, so it just gives us 1. So, oops. So if we put in some numbers here for this, and that comes out to be around about 0.53 newtons. Yeah, so that's 2 sig feet. And then on BC, it's kind of the same thing. We have the magnetic field strength times the current. Now it's just the length of wire BC. Again, the angle between the current and the field is 90 degrees. So we're going to chuck in 90 degrees. And that's approximately 0.13 newtons. And finally, we can say, well, since CD is parallel, whoops, not R, is if CD is B I L CD times sine of 0 degrees. Sine of 0 degrees is 0, so this becomes 0 newtons.